Okay, so we will continue. Okay, so so yesterday we were actually discussing on maybe how we can generalize the Bayesian decision theory of for a single feature to in different cases and also for two classes to multi classes, etc. Okay, so we have seen the four maybe sections under which we can generalize it, and we were discussing maybe these two category classification, and we have seen maybe we need a decision rule. Okay, so that is actually defined in terms of the maybe either probability or maybe a risk if you are actually considering the loss associated with it, taking maybe say decisions. Okay, so all those things we have seen yesterday, and then so here we have maybe defined actually the loss. Okay, so in terms of maybe the parameter say lambda. And so if you look into this particular equation, we can see that is, for example, lambda 1 1 and lambda 2 2. So they are actually class 1 predicted as class 1 and class 2 predicted as class 2. So that means the action is actually corresponding to the same original, maybe the class. So usually we can say that they are going to be, say, for example, when we assign a loss function, as we have seen for the maybe this particular loss function. So that is we have a 0 and 1. So 0 1 loss function we have C. So where we have either 0 or 1. So that is this particular case. Okay. So here we can say that lambda 1 1 and lambda 2 2. So there we assume that we don't have any losses, so we assign a value of 0. Okay, so this type of okay, so that is the case. And we have maybe lambda 1 2 and lambda 2 1. So they are actually the two different cases. That means two wrongly predicted as, say, for example, 1 and 1 wrongly predicted as 2. So that depending upon the severity of the maybe the wrong decision. Okay, so for example, if it is in a say I mean the say for example medical cases, so for example an HIV positive is really positive but predicted as negative. That is one possibility. The other one is actually really negative but it is predicted as positive. So there are two say such maybe two scenarios. Okay, similarly for any other problem. So accordingly, depending upon the maybe the severity or maybe the wrong classification or the cost of the wrong classification, we will be assigning different values for the loss. Okay, and so if you look into this particular equation or maybe with respect to the likelihood ratio. Okay, so we can say that lambda 1 1 and lambda 2 2 are going to be almost say similar. So that means now this is going to be maybe the lambda 1 2 and lambda 2 1 are going to be the deciding factors. Okay, and we assume that usually lambda 2 1 will be greater than lambda 1 1. Okay, because the denominator. Okay, we assume that because loss is going to be in this particular case always going to be greater than the maybe the correct predictions. So that means that time will be positive only. Okay, so that is one point. And another one is now we have to see what is lambda 1 2 and lambda 2 1, and accordingly we will have maybe the value of maybe likelihood vary. Okay, so that will be more okay in one particular case and maybe lesser in another case. So that is a analysis that we can actually make in this particular equation. So if we go to for example this particular graph, I think we have a earlier we have seen maybe a probability distribution of this kind. I mean this particular case. Okay, maybe for a particular prior probability values we have seen how the posterior probability plot will look like. So if you look into this particular maybe posterior probability distributions, we can see that in some regions, so for example, if you take this region, this corresponds to maybe say W2. Okay, so that is this is W2 and this is say W1. Okay, so that means here you can say that the larger value is actually okay W2, and when you come to this particular region, okay, we can say that that corresponds to W1. Okay, and again it becomes W2, and then it becomes again say W1. So that way we have actually different probability values, okay, and so the different x values, okay, for which, because along the horizontal axis we have the single feature that we have considered. So for different ranges of maybe the x value considered here, or the feature value considered here, we have maybe the regions where we predict w1, and in some other regions we predict as w2. Okay. So that is actually one point we have to look into this particular maybe say plot. And so the regions where maybe the area where, okay, we define, say for example, predicted as w1, usually we call it as a decision region 1. And say for example, for w2 region, we'll say that in decision region 2. So in that region, maybe for all x values, okay, we will have a maybe the class predicted is w1, and in another, say in all the r2 regions, then we'll have the decision region is going to be w2. So that is another point we have to keep in mind. So based on that particular point, so when we come to maybe this case, so that means this particular plot, okay, and so we can say that this is corresponding to the likelihood value, okay, plotted against the x value. So this is a likelihood plot, okay, and with the feature value that we considered in the previous maybe say plot, okay. So if you look into this one, we can say that there is a similar to the previous maybe regions that we have identified. We have an R2 region, followed by an R1 region, again followed by an R2 region, and then followed by R1 region. So that is this plot is also similar to exactly, okay, the regions are actually maybe similar to the previous plot. So you can say that the likelihood is also correctly, okay, maybe distinguishing that regions. So that means we can plot maybe, so depending upon, okay, maybe this suppose we are using 0 1 loss functions, and for the time being, let us assume that is for example one case where we have a lambda 1 2 is greater than say lambda 2 1. Okay, so that means we know that that is actually say this numerator is actually okay, because lambda 2 2 and lambda 1 are going to be the same. So if lambda 1 2 is actually greater than lambda 2 1, okay, so then we can say that that will have okay, maybe larger but I mean the likelihood ratio, and if it's other way, then maybe correspondingly we'll have a deviation in the likelihood, okay, value. So that means if you look into so for example, we define a threshold value for the right hand side of this equation. So let us take it as a theta. So we can have many possibilities, theta a, another one threshold, theta b, another one theta c, etc. Okay, so the so for example, suppose that theta a, okay, we are saying that okay, all these are actually say this term maybe is 1, so probability of w2 by probability of w1. And okay, so in that case, suppose the plot is actually something like this one. So that is theta is actually this particular maybe the threshold, okay, likelihood value. So that means correspondingly we can say that these regions are actually defined. And suppose we are having we are assuming this particular relation, and we define okay, theta b, okay. So in that scenario, we can say that is, so that means if you draw okay line for theta b, okay, maybe similar to the theta a, we can see that say the R1 region, okay, so the R1 region is going to be reduced, okay. So that means so the line will be something like here, and it will be here. Similarly, this line is also shifted to this line, okay. So that means we have more points actually defined as maybe W2, okay. So accordingly, that threshold is varying. Just to get an idea, we'll have maybe the decision regions, okay, for different values of x. And we can see that here so the regions are actually not simply connected also. So that means you can say that R1 is some part of region, decision region is here, and the another set of here only. and this is R2, and R2 is also okay, maybe splitted. Okay, so that way also it is possible for maybe the decision regions. It need not be always okay, maybe contiguous in say maybe in the shape. So this is actually maybe a few things that we can actually maybe analyze based on this likelihood and other things. Okay. So now we will go to I mean, we will discuss some other maybe topics, okay, which are going to be maybe generally we can say that we are specifically going into define classifiers. Maybe one of the generally used, okay, most widely used way of maybe describing this classification problem. Okay, so that is actually about okay, about so we are actually considering multi-category cases. Okay, so that is we are having we say c number of maybe say I mean the number of classes, okay, and we define a function called a discriminant function, okay, maybe a function, okay, f a say g of x, okay, so that means g of x is actually okay the function that we define for the discriminant function, and which will be used, okay, or the value of that particular function will be used for a decision making. Okay, so and we will bring in the Bayesian maybe decision rule that we have seen also into the discriminant function, because the discriminant functions are going to be general, and so when we study say artificial neural networks, also discriminant functions will be applicable, and when we study say for example a support vector machine, also this is applicable, and when we discuss Bayesian classifier, also this is applicable. So that is the discriminant functions are actually a general function that can be used for classification analysis. Okay, so here we assume that the set of discriminant functions are actually okay defined as g of x, okay, for I is equal to 1 to say c classes, okay, and so here we are actually assuming that more than two number of classes. So how we make a decision, okay, so x is a given feature vector, okay, x is a given feature vector, and so what we will do is we will assign, okay, a feature vector x, okay, to a particular class wi, okay, looking at this particular say case. So that means we find out say gi of x, okay, and gj of x such that j not equal to I, okay. So that means we will consider, suppose it is 1 2 3, there are three classes, then we will consider 1 2 and 1 3, we will not consider 1 1, okay. So that means and so for which I maybe that is actually greater than, okay, all the remaining maybe say j values, okay, we will have maybe that particular class is actually assigned, okay, to the given feature vector x. So that is actually the concept of discriminant functions, okay. Okay, we'll continue. And this discriminant function actually we can actually represent, okay, maybe in corresponding to the maximum posterior distribution also, okay, with respect to maybe the say Bayesian decision, okay. So that means we can say that j of x is equal to probability of wi given x, maybe in the case of Bayesian decision, okay. So this is a general way how this will be used, okay, but with respect to Bayesian, for example, we can say that a GA of x can be the posterior probability. So maximum discrimination, because this is a maximum discrimination, that is for which GA of x is actually the largest. So here we can say that that discrimination corresponds to maximum posterior probability. So that is actually the concept. Okay, and similarly we can as we have just represented the decision rule, okay, in different ways we can maybe this can be substituted with the conditional probability into maybe the prior probability equation, okay, keeping in mind that the evidence is ignored because that is going to be a common, okay, for the all the x value, okay, because we are considering a single feature vector. For the same feature vector, we are discussing all this. So this is a way we can represent in an alternative fashion, and this is maybe suppose we take a natural algorithm, okay, on maybe say of this one, okay, then we will get maybe g of x, maybe ln of probability of x given wi plus ln of, okay, probability of or the prior probability. So this is a way we can have, because some of these notations or equivalent notations will be, or the equations will be better suited for maybe in some cases or instances where situations where we can actually have a maybe easier analysis. So that's why we are just looking at in a different maybe say cases. So, so whatever we have actually just discussed, that means the multi-category case and different discriminant functions. So that can be maybe represented, okay, as a, for example, a general pattern classifier, okay, can be maybe represented like this one. So we are assuming that we are having an input. So the flow is actually from the bottom to top in this particular diagram, okay. So we can say that we have a d-dimensional say input vector, okay. So the capital X, maybe the components are x1, x2, etc. up to xd, okay. And suppose that we are having c discriminant functions that is corresponding to each of the classes, okay. And then so we have actually maybe action is actually the classification task, and we can actually associate with a cost also to each of the maybe if you wish you can associate the cost also to each of the decision made by the individual maybe the discriminant functions, okay. And usually we will take an action based on the maximum value generated by g1 of x, g2 of x, etc. up to gc of x, okay. So that is actually maybe the way how we can have a general statistical pattern classifier looks like. We will see a similar maybe arrangement or similar way in which the decision is actually made in different situations maybe later point. So this is maybe what is in general we can draw like this one, represent like this one, okay. So that means we can say that the feature space, okay, here the feature space is nothing but if it is a d-dimensional, we have a Euclidean space of, say for example, it's a d-dimensional r raised to d, okay, that is going to be the the feature space, okay. So we can say in a C category cases, that is divided into C decision regions, okay. So that is an important point, as we have just seen with R1 and R2 in the previous case. And so that means suppose for g of x is actually greater than gj of x for all, okay, j value which are not equal to I, then we say that the given feature factor actually lies, okay, in the region say ri, okay. So it can be r1, r2, or r3. So that is a meaning that should be kept in mind, okay. So that means it means assign x to wj, okay, because corresponding to each category we have a decision region, okay, which is represented generally as a ri. And so when we come to two category case, okay, again generally two category case is a typical maybe case, okay, which is actually maybe a widely used scenario, but maybe for on an analysis side also two category class is actually maybe easy to, okay, maybe the best way to maybe make the analysis or the concepts can be conveyed in the easiest way. So that's why even though we are having general cases, two category cases actually discussed specifically. So when we call this two category, okay, classifier, we call this a dichotomizer, okay. So which is actually we can have a two discriminant functions, say for example g1 of x and g2 of x, okay. So usually we can say that if it is g1 of x is greater than g2 of x, then we say that the x corresponding to w1, and if it is g2 of x greater than g1 of x, then we say that x corresponds to maybe region r2, which corresponds to w2, okay. But whenever we have a two category case, we don't need actually say two discriminant functions, but okay, using the two discriminant functions, we can define a single maybe a decision function, okay, which is actually nothing but the difference between g of x and g1 of x and g2 of x. So that way, maybe we can simplify the case, okay. And now looking at the value of g of x, so whether it is positive or negative, we can say which one among this g1 of x and g2 of x is actually maybe larger, okay. So that means if g of x is greater than 0, okay, this g of x is greater than 0, that means a positive value, then we can say that you have to decide it as w1, okay. Otherwise, if this is greater, then we can say that this value will be negative, less than 0. So that means we can say we have to make a decision for w2. So that is maybe a simplified case, okay, especially in the case of two category cases. But from 3 onwards, we'll have a we are not interested in that way of simplification, but we'll generally for g1 g1 of x, g2 of x, and g3 of x. So that is a special case of maybe two category case. And here also we can have maybe say the g of x actually maybe replaced by the previous equations that we have seen, okay. Maybe so that is, yeah, g of x is actually we have g1 of x minus g2 of x. So that means we can substitute this one, and correspondingly the if you are taking the natural logarithm, then we will get this equation. So this is actually a rearranged, okay, equation by substituting the condition probability into prior probability here, and you will get this particular expression, okay. So that is one thing. And this is actually suppose we plot the two functions, okay, for g1 of x and g2 of x, okay. Suppose the probability distributions are like this one, or the decision regions are actually like this one, okay. Then we can say that so the top maybe you can say that there is a crust like okay, that the top portion of this figure that represents a probability distributions, and but the bottom, okay, they are actually just maybe their projections, okay, or maybe how the decision regions will look like, okay. So that is specifically for two category classifier, okay. So the probability densities are actually shown at the top, okay. And so this also we have seen, okay, maybe say for example in this case we have r1 is actually, okay, maybe this middle region, okay, and the we have R2 is actually maybe separated. So that you can actually see in the top figure also, because there is a red region here and there is a red region here also. Okay, so that means that's why we have a majority of R2 comes here and there is some portion of R2 comes here. Okay, but R1 is actually maybe in this particular maybe mode. So that's why this particular mode. Okay. And the ellipses actually maybe represent, okay, 1 by e times the peak of the distribution, okay, maybe to just represent maybe where is the highest peak actually say comes. So that is no, we are not interested anyway. This is a pictorially how these distributions will look like, and maybe, and we can say that the decision boundaries are there. So decision regions are we have defined it. So decision boundaries are nothing but maybe the lines or curves or okay, that separates, okay, maybe the decision regions. So that is how maybe a plot of maybe this probability density functions will look like, and the corresponding maybe the decision regions, okay, and their projections actually, okay. So that is another point you have to keep in mind. And so before going to the next one, so we have actually we'll come to this point once again. I mean, I think just wait a moment. Yeah, in this particular equation, actually, maybe yesterday we have seen that is we are assigning into say this loss function, okay. and then we can actually define the risk associated like this one. And okay, this is j is equal to 1 to c, but we have a, whenever we have a I is equal to j, okay, we have a 0. Okay, so that means corresponding lambda values will become 0. So that means whenever we have I not equal to j only, we have a this particular say probability into that lambda term. Okay, that is this particular risk is actually defined. So that means that's why we have this equation I is equal to, okay, I not equal to j, we have a probability of wj given x. Okay, so this is actually this is a risk, so which we are actually trying to minimize it. Okay, so that way of using this particular zero loss function, whenever we have such a maybe a reduced representation, we generally call this particular classification as a minimum error rate classifier. Okay, minimum error rate classifier. So generally whatever we have discussed. Okay, and this is actually we are actually predicting x the given feature vector to wj. So then the corresponding maybe we can write this as equivalently as, okay, but we are actually trying to minimize this particular probability for wj, and which is equal to 1 minus probability of wi given x. So because wi and wj are actually the two cases, the probability or the classes that we are actually discussing. So that means in order to have in order to reduce this risk, either we are actually minimizing wj, or in order to or we can say that maximizing wi, so the probability of wi given x. So that is another interpretation that we can actually get from this particular equation. Okay, so that is the case, because only if we maximize this one, this term will be minimized, so that this is also minimum, equivalently this is also minimum, so the risk is actually minimized. So that is another point that you have to keep in mind. Okay, so that is the case. And okay, then the remaining is actually maybe nothing but the all these equations we have already say seen. Okay, maybe just to corresponding, okay, risk, then the probability, and maybe the other cases. Okay, so that is actually about maybe okay. So here this also we have seen the discriminant functions corresponding to maybe, okay, maybe so when we actually have a discriminant functions, when we apply for Bayes classifier, okay, so we can say that we are actually maximizing maybe uh, the I mean the discriminant function. So that is actually we have the risk we are actually trying to minimize, so it is minus, okay, risk that we are actually trying to say maximize. So that is a corresponding equation for actually the discriminant function and the risk, okay, that we can associate it. So that is a case. Okay, and this is correspondingly, okay, what is going to be, if it is a, we are considering 0 1 loss function, then we know that the risk is actually maybe the probability value. So then corresponding, okay, this one is actually discriminant function is okay, this expression. Okay, so that is this also we have already discussed it. Okay, maybe, okay, so all these we have just discussed. Okay, this is a decision regions and boundaries. Okay, so there can be R1, R2, etc. up to RC number of decision regions. Okay, and they are separated by the decision boundaries. Okay, and one more thing, when you consider a decision boundary, okay, between say G1 of x and G2 of x, we can say that in that decision boundary, G1 of x will be equal to G2 of x. Okay, because the boundary regions are, we can say they are maybe either the decision is can be undefined, because a point falling on the decision boundary can be can belongs to either region 1 or region 2. Okay, so that is the property of maybe a point on the decision boundary. Okay, so that is another point we have to keep in mind.
Sorry, sir.
Yeah.
Can you go to the above slides? So 2 slides above. Uh, one more. Yes, sir. Sir, can you explain this point, the general loss function again?
Yeah, this is nothing but so say actually we are trying to maximizing okay this particular say discriminant function. So here in the case of Bayes classifier with respect to risk, we are actually representing the definition of I mean the discriminant function is actually minus of the risk. Okay, so
Okay.
that is actually the way the for a general loss function, how the discriminant function is actually defined with respect to Bayes classifier is this is a definition. Okay.
So, sir, the negative value, if it increase the risk, the negative value will increase. So, proportionally, the general loss function will also increase.
Uh, so that is uh, so the risk is actually we are trying to minimize, right?
Yes. Okay, okay, sir.
Okay.
Both are
So
proportional.
yeah, that is why it is like that negative. Okay.
Okay, sir.
Okay. Okay. So that is the case. Fine. Okay. And I think so with that actually we are actually coming to end of another section which we have actually maybe so this discriminant functions and corresponding things are going to be coming, we'll be discussing later also. And and one more thing about the Bayes classifier is say for example we'll come to generally just wait a moment. Okay, so usually maybe when we consider a data set, okay, when we consider a data set in say machine learning problem, okay, so this is one a typical way of maybe representing data, okay, where corresponding to say for example we have a x1, x2, okay, etc. up to xn, okay, so n number of features or and we have a maybe a class information, okay, that is a way usually in tabular form a data set is actually represented okay in a machine learning problem. But there can be other representation, graph representation, image also you can actually convert into maybe this particular form, but image is a separate, different type of maybe data, input data. And maybe we can have a tabular representation where the features are actually the columns, okay, and the last column we will say that that corresponds to the category information, okay, w1, w2, etc. say wc, okay. And each of these rows are going to be okay, so one row corresponding to maybe one feature vector, okay, which is actually say x1 through maybe xn, okay. So if you plot in a raised to d space, then that corresponds to one point. Okay, so x1, x2, the x1 value, x2 value, x3 value, like that. That corresponds to one row, corresponds to one data point in the space, in the feature space. So that's why the concept of feature space and maybe how a typical data set can look like. But there can be other way of input data. Okay, and okay, and so usually we assume that okay we have this x1 is actually independent of x2, okay, similarly x2 is independent of x3, all these are actually independent each other, okay. So this the features are we consider as independent of each other, okay. And we assume that they are identically distributed also, okay. So we will discuss that concept later. So the name-based classifier usually a Bayesian classifier that assumes that these features are actually independent, okay. Then when we apply okay this particular decision rule that we have discussed, then we call it as a name-based classifier, okay. So that is a typical classifier, okay, where we assume that these features are actually independent. But we know that in reality the features may be dependent, okay. There may be close relationship in many cases, and there can be independent also, so, okay. So the naive means it is assuming that the features are simply independent. So that is maybe a name that you will come across, okay, but what we have discussed is actually a general Bayesian classification, okay, where it can be in both cases. So that means either it can be independent or say dependent. But we will discuss that maybe later. But keep in mind that there is another term that you can come across is naive based classifier. Okay, so maybe we will see that later. So this is another point that we should maybe to discuss. And actually, what is we will discuss in the next class is so far we have assumed that this probability density functions we have discussed. And now what we will we have actually not discussed on maybe what way this probability is distributed. Okay, maybe the shape of their maybe the say their plot. Okay, their distribution looks like it. Okay, so now what is going to remain is we will discuss how a probability distribution may look like, what are their characteristics, and we will be discussing that with the normal density. Okay, I think you might have studied about the normal density or Gaussian distribution, okay, or bell-shaped curve, etc. And then we will see the other maybe portions like maybe how we can actually really estimate maybe the density or the probability density parameters. So that is what is actually we will discuss in the next class. Okay, so today we will stop with this one and we will continue from next class onwards. Okay, thank you.